AC to AC conversion. We have covered the AC to DC conversion portion, which are normally called as rectifier, in which we have covered the single phase rectifier. It consists of two portions. One was the control rectifier portion, and other was uncontrolled rectifier portion. And then later on, we have studied three phase rectifiers. In it, we have also studied the control rectifier and the uncontrolled rectifier. So after that, we are going to study the DC to DC converter. So basically, DC to DC converter are those converters which actually whose input is also DC and whose output is also DC. Normally, the DC supply cannot be step up or step down through a normal transformer because of no frequencies. So special circuit or converter are used in order to step up or step down these voltages. So in this lecture, we will study about these converters, how we can step up or step down an input of DC voltage to output of the same DC voltage to a different values. So that's actually our today's lecture. So these are the course outlines. We will go through some of the basic converters or DC to DC converter. Normally we have one is the
सर आपकी आवाज़ बहुत स्लो आ रही है
also
सर.
called a step down converter. These are those converters which actually step down the DC power supply. I mean, if its input is 10 volts, so the output will be less than 10 volts. So these are called as buck converter. Then the second one is boost converter. These converters actually step up the input. चलो ठीक है, लेट्स कंटिन्यू. कोई प्रॉब्लम हो तो खैर चैट में कर लें. आई थिंक सो वॉइस अभी क्लियर हो. We were actually discussing the basic DC to DC converter. Uh, what are basic to DC? What are actually basic DC to DC converter? We have already studied this converter in the first lecture, in which we were given a load that was rated at 100 volts and a source that was rated, a load that was rated at 50 volts and a source that was rated at 100 volts, and we want to connect it, but the connection was not possible as the load rating was lower than the supply voltage. So one solution was to connect a variable resistor, and its setting was like that half of the voltage will be dropped across the resistor and half in the load, so load can be turned on. But in that case, the efficiency was not that much good. Later on, we have introduced a a transistor in that circuit, but still we were considering the efficiency, so the efficiency was not that much good. In the third step, we have introduced a single pole double throw switch, and the switch can change from position 1 to position 2. The position 1 and position 2 timing were actually depend upon the switching, for how much time we want to connect it to position 1 and for how much time we are connected to position 2. So in that case, when the switch was at position 1, the load was getting a voltage of 100 volts, and when the switch was connected at position 2, the load was getting voltage of 0 volts. So later on, when we derive its average voltage and set the value of the switch at of D equal to 0.5, so the load actually turned on, and the load was in that case the efficiency was also improved. So that was the case in the first lecture, and we have already studied that is actually a simple step down converter. So this is the basic step down converter, and there is a single pole double throw switch is used. So the switch can connect to position 1 and position 2 depend upon for how much time it can be, what are the requirement of the load side. Normally the duration of the switch is from 0 to 1. The maximum duration is the 0, and the minimum duration is 0 and the maximum duration is 1, and D is the duty cycle. So it means when the D is 0, it means the switch 0 is connected, and when the D is 1, it means the switch 2 is connected. So its values can be changed. The D value is variable. Its value can be in between 0 and 1. So so in that case, when the load is connected, when the D when the D is when the switch is connected at position 1, so the load was getting a voltage of Vg or V, so and multiply by the DTS. DTS is the time duration of for how much time the switch is connected at position 1. And when for that case, when the switch is connected at position 2, so the load was getting a 0 voltage. So when we take a Fourier series of this value of this area, so we get a value of dVg. We will get a value of dVg, which is the average voltage of this area. Now this is a low pass. No, this is a step down converter, DC to DC converter. We have already studied that due to the switching changes, there are some ripples that actually arise in the circuit. So if you want to eliminate these ripples, we have to install a low pass filter consisting of inductor and capacitor. These ripples will be eliminated through these filters, and the load will receive a favored DC voltage. So this is actually the output voltage that is actually equal to dVg. So if we take the average value, if we take the Fourier series of this area, we will get dVg. So Vs is equal to dVg, or we can say that V is equal to dVg. Now V is the output voltage, Vg is the input voltage, and D is the duty cycle. So D defines for how much time the switch is connected to position 1 and or connected to position 2. The maximum value of the D is 1, and the minimum value of D is 0. So if we look at this graph, so when the D is equal to 0, the Vg voltage is 0, and when the D value is equal to 1, the output voltage will be equal to the Vg. So it means that we can get a output voltage from 0 up to the input voltage, the input supply voltage. For example, if the input voltage is 10 volts, so the output voltage can be from 0 to 10 volts. If we set the D value to 0.5, the output voltage will be 5 volts. If we set it to 0.9, the output voltage will be 9 volts. So if we set it to the maximum value of 1, D value is 1, so the output voltage will be 10 volts. Or if we set the D value to 0, a minimum value, so the output voltage will be 0. So it means that from a DC to DC converter or buck converter, we can get a variable output voltage from 0 to the input voltage. Its value can be from 0 to the input voltage depending upon the value of D. Now, actually, what is the operation of the basic DC to DC converter? When there is no switches are used, when there are no semiconductor devices are used as switches, so this is the normal circuit of DC to DC converter, a buck converter, where a single pole double throw switch is used. But if we want to replace the single pole double through a switch through a semiconductor device, in order to facilitate the automatic switching and in order to facilitate the efficiency, we will install a MOSFET and a diode. So the MOSFET will be controlled from the gate, where a PWM modules will be used from where the gate can be controlled. The MOSFET gate can be controlled. So when the MOSFET turns on, the diode will remain reverse bias. It means the switch 1 is connected. And when the diode become forward bias and the MOSFET gate gets 0 voltage, so it will go through the reverse bias and it will remain turned off. So it means the switch 2 is connected. So we can actually switch that single pole double throw switch into this through these semiconductor devices. They can operate as a switches, the MOSFET and the diode. So what are their analysis, how they operate, how the energy is transferred, where are the small ripple approximation, where are the derivation. So we will go through this process. So first of all, what is the actual output waveform of a buck converter? So that is actually a buck converter having a low pass filter. The actual waveform is like this, that is shown in the figure, where the output voltage consists of the output voltage plus some of the ripples. The ripples, ideally the ripples can be eliminated, but practically there are some of the ripples. If the voltage is 100 volts and and there are 1% ripple, it means 101 and 101 and 99 volts, means there are 1 volts and minus 1 volt ripple are there in the output voltage. So the actual waveform will consist of ripples and the actual or DC voltage. Now we want to eliminate these ripples. So these ripples can be eliminated, but can be eliminated. Then can be they can be minimized, but they cannot be 100% eliminated. So if in a well-designed converter the output voltage the ripple should be small, the waveform in the output waveform the ripple should be they can be minimized, the ripple can be minimized that, but they cannot be eliminated completely because it's a practical condition. So what we will do, we actually apply a small ripple approximation in which we consider that the ripples are actually not present in the output, and we just ignore these ripples in the output voltage, and we just consider that the output voltage is actually power DC. So this is called actually a this is actually called a small ripple approximation. So it means that the Vt as in the first case was equal to V plus V ripple, but we apply small ripple approximation in which we consider in which we ignore these ripples. So when these ripple are ignored, it means that the output voltage is now approximately equal to the power DC. So we can say that the Vt is equal to V. So this condition is called a small ripple approximation. Now, what are the analysis? How the switches are actually connected? What are their voltages? What are the inductor voltages? What are the capacitor current? First of all, the switch position 1. When the switch is connected at position 1, this type of circuit is actually the inductor is connected to this voltage and the capacitor current flows. So when the switch is connected at position 1, this type of circuit is formed. And when the switch is connected at position 2, the source voltage is disconnected to the load side. So this type of circuit is formed. Now let's go through their analysis. We are interested in the inductor voltage and the capacitor current. So we will derive an equation of inductor voltage and capacitor current, and in later on we will apply the charge balance condition and voltage balance condition on these equation. So first of all, when the switch is connected at position 1, if we look at this, what is the inductor voltage? So if we apply a KVL over here, we will get Vg equal to VL plus Vt, or we can say that Vt is equal VL is actually equal to Vg minus Vt. This is actually this is actually the inductor voltage. Now we here the input voltage, here the output voltage consists of this is actually AC, as this consists of some of the ripples. So the output voltage is in the small form, but the input voltage is in the bold form. It means the input voltage is DC, but the output voltage consists of ripple. That is why it is still not power DC. So we have considered, or we can apply a small ripple approximation. When we apply small ripple approximation, so what will become, what this equation will become, VL is approximately equal to VG minus V. So what is V? V is the output now, which is actually now power DC. So the small approximation actually states that we actually eliminate, or we actually ignore the ripples in the output. So we can apply these conditions to these circuits. Now, what is inductor voltage actually equal to? Inductor voltage is actually equal to VL is equal to L di of L dt, where I of L is actually the inductor current. So we can say that VL is equal to L DIL of dt. Now put this in this equation. So we will get VL is equal to DIL divided by dt equal to VG minus V. And what is actually DIL divided by dt equal to? This will be equal to VL of Vg minus V divided by L. If we transfer, or if we transfer this L toward this side, so this equation will become DIL of dt equal to approximately equal to Vg minus V divided by L. So the inductor current changes with an essentially constant slope. So this is the inductor change actually. This shows this di by DIL divided by dt shows the inductor changes, how the inductor current changes when the input voltage is applied. So this is the position 1. When the position 1 is connected, this is the inductor voltage characteristics. Now, when the switch is connected at position 2, so when when the switch is connected at position 2, what is the inductor voltage equal to? The inductor voltage now equal to VL is actually equal to minus VT. VL, if we apply KVL over here, VL is equal to minus VT. Then apply a small approximation on this equation. So the VL is approximately equal to minus V, where V is the now after approximation is the DC voltage. Now we already know that VL is equal to L divided by dt. So put this equation in this equation. So we will get L divided by dt equal to approximately equal to minus V, or DIL divided by dt approximately equal to minus V divided by L. So this is the inductor current changes with a essentially constant slope. So this actually shows the current change in the inductor for the when the switch connected at position 2. This was the equation for the current change in the inductor for position 1, and this was the current change in the inductor current when the switch is connected at position 2. So if now what we will do, we will just draw its waveform that when the switch is connected at position 1, so the time was 0 to dts. So what is the waveform of the inductor current, and when the switch is connected at position from dts to d, what was the waveform, or what is the inductor current? So from the inductor current waveform we can know the behavior, and after that we can apply the Fourier series on that waveform. So this is actually the waveform. So if we look at the waveform, so VL current is equal to Vg minus V from dts, as we have already derived this, that the inductor current is equal to Vg minus V. So Vg minus V, and for this when the switch is connected at position 2 means from dts, from this was 0 to dts, and this is from dts to ts. So the current was minus V, that is over here, that is VL is equal to minus V. Or what is this was the inductor voltage. Now what is the inductor current equal to? This is the inductor current. The inductor current actually rises for in the first duration from 0 to ds, and after that when the switch is connected at position 2, the inductor current actually decreases. After that the inductor current increases again when the switch is connected at position 2. So this is the waveform for the inductor voltage for each position 1 and 2, and this is the inductor voltage behavior for position 1 and position 2. Now what we want to do, we actually uh, want the inductor current ripple magnitude, that how much ripple are actually there. So what are the changes? Here are two changes. One is this delta L, one is this one change, another is this one change. So it means change in current of IL, that is equal to delta IL, that is equal to Vg minus V L divided by T. As this current changes from over here, if we this is the actually DC current. This was the required DC voltage current, but the current changes, and the current changes from negative to positive. It means double changes are there. So we can say that the slope, the change in the current is 2 delta IL, that is actually Vg minus V divided by L multiplied by the duration, that is T dts. So slope multiplied by the length subinterval. From here we can derive the current, the inductor current ripple is actually equal to what, Vg minus V divided by 2L dts. So if you want to derive the how much ripples are there in the inductor current, you can derive it from this equation. As you know, the input voltage, output voltage, the inductor current value, inductor voltage, inductor magnitude, and d duration of the switching. So when we put these values, we can identify that how much ripples are there in the output or in the current of inductor. Now what we apply now, the inductor inductor voltage second balance on these equation. One equation we have already equation that was actually equal to Vg minus V divided by L, and other equation was minus V divided by L. What is inductor voltage balance? What is what is actually equal? What is actually the principle of inductor voltage second balance? Actually state that in steady state the net change in the inductor current is actually 0. So we can say that this was actually the this is actually the equation of inductor voltage, that VL is equal to LdIL divided by dt. So now we can say that the change in the inductor current in a periodic steady state is actually zero. Mean there is no change in the inductor current in a steady state. So we can say that actually the DIL divided by dt is actually zero. Or we can also say that the total area under the inductor voltage waveform is zero whenever the converter operates in a steady state. So when there is a current change, there will be no there will be a change in the inductor current. But when the converter operates in a steady state, then the net change in the inductor current will be zero. So we can apply this condition to the position 1 and position 2 equation. Like we have like this was the waveform that we have derived. So what we will do, we will apply a Fourier series over here. So v of L is equal to Vg into integral of 0 to dts, then minus v integral from dts to ds. So we apply integral over here on these thing. This is actually Vg minus V into dTs, and from here we get V into 1 minus dTs. So the average voltage is equal to VL is equal to dVg minus V or plus d dash minus V. So now apply the small now apply the steady state condition. That in steady state condition the inductor voltage is equal to zero. So it means this side will be equal to zero. From here we get dVg minus d plus d dash into v, where d dash is equal to 1 minus d. So from here, if we simplify it, we get dVg minus v, or actually this is equal to v dVg, where v is the output voltage, d is the duty cycle, and vg is the input voltage. Now, this is the output equation, or this is the output characteristic of this buck converter, which actually shows that this converter actually stepped down the DC voltage. So as if we know the ratio, the output to the input ratio will be equal to D. V divided by Vg is equal to D. So this actually from this equation we can actually this equation actually shows that the output voltage can be stepped down depending upon the duty cycle. So these all derivation was for the inductor current voltages. Now now we want to derive expression for the capacitor charge balance, as what is IC equal to? IC is equal to CdV by CdT, and we can say the other condition in that in periodic state the net charge in the capacitor voltage is zero. In the inductor there was, what was the condition? The net charge in inductor current is zero. But in case of capacitor, the condition is that the net charge and capacitor voltage is zero. So these are the steady state condition. Or we can also state that the total area under the capacitor current waveform is zero whenever the converter operates in the steady state. So the average capacitor current is then zero. Whenever the converter operates in the steady state,